Hi there. So in this video, we want to start talking about three-dimensional coordinates. And so this is getting into math in three dimensions, and we'll even extend some ideas to even higher dimensions that we can't visualize. And so this is an exciting topic, and we just have some basics to cover. We're going to talk about how to work with coordinates, how to set up coordinates in three dimensions, and how to work with them, and then talk about some basic formulas associated with them. Okay, so here we go. So one way you can start visualizing a 3D coordinate system is think about a room that has a corner in it. All right, and I just found a image that is actually tiled too, so it'll help. And so we can visualize this room right here. So now, where that corner comes together, we can think about that as being the origin. Now notice that where these walls come together, those form lines, right? Like that. And so we can think about those as forming our axes. And so I can draw a line that goes along there, okay, and a line that goes along here, like that, and a line that goes along here, like that. Now I'm going to pause for a second to draw those a little bit better where I can use a ruler. All right, not that I still didn't do the greatest, but at least better than what I had. Now, notice that I have three axes now, so that's going to tell us that we're going to have a third coordinate or another axis that we'll call the z-axis. Now, I'll explain this later in the video, but in this kind of typical drawing, we'll call this the x-axis, over here will be the y-axis, and over here will be the z-axis. You don't have to label that way, it's just a kind of a standard way to label things. All right, and so since I have three axes now, what does that tell me? That tells me that I'm going to have three coordinates to work with. Okay, and so we're going to have an x and a y and a z coordinate now. All right, and so let's just think about trying to plot a point like the point 6 comma 4 comma 3, like that. All right, now you can see here I need to start making tick marks on each one of my axes. Back here, I'm realizing a downside to using this image is it's a little obscure in here, but make sure you realize you can take advantage of this area right in here too. Okay, and so to see those tick marks, right here would be the first tick mark on the x-axis, right there, and then there's x equals 2, there's x equals 3, there's x equals 4, 5, and 6. Okay, and then on the y-axis we have y equals 1, y equals 2, y equals 3, y equals 4. All right, and so now you can think about, we can go out here where y is equal to 4 on that tile line, and we can come out here where x is equal to 6 on that tile line. Okay, and so this is the point right here down in what's called the xz plane that I'll explain in just a moment. Okay, so that's just how you would plot the xy coordinate. All right, now this is where drawings get a little bit strange because there can be some a little bit of perception error, because what we're really trying to do, we're trying to visualize a three-dimensional object, but think about it, you're on a screen, that's two-dimensional. Okay, and so it can get a little bit hard to read this, and I'll admit three-dimensional drawings aren't the easiest to deal with, but basically we think about going up 3 units on the z-axis. So about here would be 1 unit, like that. About here would be 2 units, so about right here would be 3 units. And so to plot the point 6, 4, 3, it would look about like that in space. Okay, and so we would say that that right there is the point 6, 4, 3, the best we could draw it anyway. All right, and so that's the idea there with the three-dimensional coordinates. Now going back to just the main axes picture, you can notice that we have those two walls in the floor, right? Well, geometrically those would be planes. They would be just flat surfaces. And those are important planes to keep up with, okay? And so we have some basic planes here, all right? And the first one would be the plane that's down here. Hopefully you recognize what that is. That's the floor in this picture, first of all. But what two axes are determining that? We have the x-axis and the y-axis, like that. And so we call that the xy plane. Okay? Now, if you think about it, think about having a point down in here on the xy plane, just on the xy plane. okay, it's going to have an x coordinate. And I don't really feel like counting that out, but it's probably about 7 or 8. Don't worry if that's incorrect. All right, it's going to have a y coordinate that looks like it's about 5. But notice that that point is down in the xy plane. It doesn't go either up or down off of that. And so the z coordinate would be 0. Okay, so a distinguishing feature of the xy plane is that the z coordinate is equal to 0 in the xy plane. Okay, and then we have these two other planes that are the other walls. All right, and so we have this plane right here. Okay, that wall, if you want to think about it for now. Okay, what two axes are determining that plane, y and z? So we would call this the yz plane. And if you think about that, any point that's in the yz plane, it's not moving left or right at all. And so its x coordinate would be 0. Sorry, that's not 0. Okay, so you would just have these two coordinates right here, but the x coordinate would be 0. So what I'm getting at there is that for any point that's in the yz plane, we have that x is equal to 0. And you can kind of see a pattern now. If you're talking about one of these planes, the third coordinate would be 0. So likewise, over on this third wall here, right here, okay, that's determined by the x and the y axes, and so we would call that the xz plane. And in the xz plane, we have that y is equal to 0. Any point in the xz plane is equal to 0. Okay, now just a vocabulary word too. These are called the coordinate planes. All right, and so whenever we talk about the coordinate planes or a coordinate plane, then we're referring to one of those three planes, and they're very important for doing many things. Now, one other thing too, I just wanted a motivational example of using a room to try to talk about three-dimensional coordinates, but make sure you realize there's negative sides to each one of these axes. And so there's a negative x-axis, there's a negative y-axis, and there's a negative z-axis. So we could have negative coordinates as well. All right, and so that's the basics of the 3D coordinate system. Okay, now what I wanted to start talking about now is how we typically draw axes in 3 dimensions. So I'm sorry to all you lefties out there, but there's just kind of a standard way to draw axes. It uses what's called a right-handed coordinate system, or sometimes it's referred to as using the right hand rule. And so you don't have to use this, but it's very standard. Okay, now I'm going to talk about right-handed in a minute, but I want to point out something about axes, just drawing our standard axes. So typically, whenever people draw x, y, and z axes, there's two basic ways that they'll do it. Is that they'll draw two axes that are perpendicular to each other. Okay, but that's not our usual x and y axis. It's the y and the z axis. And then they'll draw the z axis or the x axis like this. And the idea is that this is actually coming straight out of the page. The problem is we're trying to draw in 3 dimensions on a 2-dimensional surface, and so there's always going to be some distortion. Okay, but the problem is if you notice on the 2-dimensional surface here, this angle and this angle aren't equal to each other, nor is this angle equal to them, and that ends up causing more drawing distortion than a lot of people like. So some people have started drawing them this way, like that, where on the 2-dimensional plane those angles are equal to each other, and it leads to less distortion. I don't mind how you do it. Okay, just be aware it is hard drawn in 3 dimensions. Some people are very natural with it and they do a great job. Guess what? I'm not. And so that's one of the issues that we'll have to deal with, and that's why I use software so much when I'm doing 3-dimensional stuff. Okay, so now the thing is, this is just kind of a standard way to draw axes, but you don't have to. Okay, you could have axes that go like this, like that, and this doesn't necessarily have to be the z-axis. Okay, the z-axis could be over here, But what the right hand rule does is it kind of gives us a standard way for how to set them up so that we're always looking at the same picture and we don't have pictures that are reversed from the way most people are used to working with. So I'm going to explain this right hand rule with a video that I hope will make sense. So I'm going to try this out. So hopefully this will make a little bit of sense. But notice right here that I've drawn my axes with the standard way that I was talking about a moment ago. And then up here I have these two images. And make sure to convince yourself that that's my right hand that I've taken pictures of. Okay, and so there's two basic positions with my hand open and then where I make a closed fist with my thumb pointing upward. Okay, first let me show you how this works with our standard drawing setup. Okay, so the idea is that to use a right-handed system, I draw my X and Y axes where I want them, and it's a way of determining where the Z axis should go. So you think about lining your hand up along the positive X axis like that, okay, and then closing your hand into that fist position. And if you think about it, whenever I go and do that, my thumb would be pointing upward, and it's a little bit off because of my image, but my thumb is pointing upward right there. So that's telling me that to use a right-handed system, the Z-axis should be going upwards. Okay, so I hope that makes a little bit of sense. So let me show you what I mean by this. Okay, and so let me, I think it's that one. No, it's not that one. It's this one. Okay, so let me rotate things around a little bit here. Okay, and say I wanted that to be my X and Y axis. Okay, and say I wanted this to be my X axis and I wanted this to be my Y axis, but I wanted to draw my Z axis so that I have a right-handed system. So the question is, do I draw it going this way or do I draw it going this way? All right, and so we need to think about the right hand rule. This one's going to be a little bit strange, but we need to line things up so that my hand points along the positive X axis. Okay, oops, sorry. All right, and so there's my hand pointing along the positive X axis. Okay, now I need to go and I need to close my hand. Okay, like that. And so whenever I do that, my thumb is pointing this direction, so my Z-axis needs to be going out this way. All right, so notice there's the Z-axis that I had drawn before. That's going in the wrong direction. So that right there would need to be my Z-axis to create those in a right-handed system. All right, and so let's just play around with this a little bit more now that I am convinced it'll work. All right, and so let's see. Let's say we draw our axes over here. Okay, and let's say I wanted this to be my X-axis and I wanted this to be my Y-axis. Okay, like that. And so then where does my Z-axis go? So I need to take my hand and point it along the positive X-axis like that. Okay, and then I need to close my hand like that. Like that, and so that's telling me my Z-axis should be going this direction right here. So which one should it be? There it is right there. And so that is where I would want to put my Z-axis to make that a three-dimensional coordinate system. So that's the idea of a right-handed coordinate system. I hope that makes sense. It's something that's a little bit tricky to understand. There's also going to be a vector operation called the cross product, and determining the direction that the cross product points uses the right-hand rule as well. And so we want to try to at least get familiar with it in some sense. All right, so now that we're through the basics, there's just some basic operations that we can do either on a single point or pairs of points that we want to make sure and mention. Okay, the two main things we're trying to get to is the distance between 2 points and the midpoint of 2 given points. All right, so but to get started with the distance of between 2 points, then first of all we want to talk about the distance of a point to the origin. All right, and so here I'm just going to talk about a general three-dimensional point. So its coordinates are x naught, y naught, and z naught. So thinking about how to plot that, you would go out x naught on the x-axis, y naught on the z-axis, and then up z naught, or down if your z naught was negative. All right, and that's just a derivation. We're going to get to a formula here in a minute, so if this loses you a little bit. But the idea is that we can draw these two lines right here and where they intersect. So this would be if the point were just in the xy plane. But the key thing is I got to make it go up z naught. So just to help me out here, that's what this line is right here. It's that height from 0 up to z naught. So I'm going to put it right there. Okay, and so in terms of what our point is right here. Okay, now what we're trying to do is we're trying to find the distance between that point and the origin. So I'm trying to measure this distance right here. Okay, and so let me see if I can get that lined up a little bit better with that. Well, there's a little bit of distortion, but it's not too bad. Okay, so you can probably take a guess that I'm going to be using a Pythagorean theorem, but it's interesting. I have to use it twice to actually get this distance right here. Okay, because the Pythagorean theorem deals with legs of a right triangle. Right now I don't have a right triangle drawn in here anywhere. Okay, and there's a key line to draw that will help us do this. And so let me see here. Let me do it with that way. And so what I'm going to do is I'm going to draw a line going from the origin down to that projection. Now it's a little hard to see from this picture right here because of distortion, but there is actually a right angle right here, and I'll explain why in just a moment. But there's actually a right angle right here. Okay, and that's the key thing there. All right, and so the reason that is a right angle, it's just you got to remember we have some distortion going on, but this line right here is dropping straight down to the xy plane. So this line and this line have to be perpendicular to each other. Now, again, just to remind you what we're trying to do, we're trying to find the length of this line right here that we would call the distance back to the origin. Okay, now, so if you think about it, the height of this triangle that I just drew, that is z naught. Okay, the problem is that I have this length right here that I don't know yet. Okay, so I'm just going to call it h, or I'll call it L for a leg, except my L's kind of look funny, so I'll use a capital L. All right, so what we have right here is we have this right triangle whose height is z naught, whose leg is L, and then D is what we're trying to find. Now, from the Pythagorean theorem, we know that D is L squared plus Z naught squared. The problem is we don't know what L is, but we have another triangle that we can take advantage of, this triangle right here. Okay, and why is that a right triangle? Where is its right angle at? Its right angle is right here. Okay, because that line from x naught extends to the is parallel to the y-axis and goes from the x-axis, and the x and y-axis are parallel to each other. Okay, and so what I need now is I need to work with this triangle right here. Okay, and use the Pythagorean theorem on it as well. And so over here I'll redraw this triangle in 2 dimensions. All right, and so we have this triangle. It's going like this. All right, hopefully you can see that the length right here, that's equal to x naught, or that's equal to y naught. Sorry about that. Okay, and then the length from here to here is x naught. So we have this, the way I've drawn it, that shorter leg that's x naught, that longer leg that's y naught, and the hypotenuse of that triangle is L, like that. And so using the Pythagorean theorem, we have x naught squared plus y naught squared is equal to L squared. Okay, so what can we do? Here we have an expression for L squared. I can plug it in over here. And so what do I get? I get that D is equal to L squared, but I'm going to rewrite it as x naught squared plus y naught squared. And then I still have this plus z naught squared. Okay, like that. And so there's our formula for the distance of a point from the origin. Make sure you realize it's the same formula. In 2 dimensions, we just have x naught squared plus y naught squared. So whenever we go to 3 dimensions, this formula just extends in a natural fashion. Okay, so now we can extend this idea that if we're given 2 points, and I'm just going to use general points right here, and we want the distance between them. What we'll see is the picture is the same, except we're not at the origin anymore. And so things will slightly change. So just to draw a diagram of this situation, think about, having points that are far from the origin just to help us. So we have these axes down here somewhere. Okay, and so I have these 2 points here. I have this point right here, and so that's the ones with the 0 subscript. Okay, and then I have this other point out here, and so that'll be the point with the 1 subscripts, x1, y1, z1. And again, I'm trying to find this distance between the two. Okay, well, it works the same way. All right, the first thing I can do is drop this leg down right here to get a right triangle. Okay, and in terms of our last example, this base length right here will correspond to that L. Okay, well, the question is what is this length right here? Right there? Well, those are heights in space. And so we started at Z naught and we went up to Z1. And so that length right there is just going to be Z1 minus Z naught. Okay, now that's key to the derivation, and you can probably see ahead if you see that. In the last, whenever we have a single point, we only used the z coordinate. Okay, but what is this measuring? This is measuring how much the z's changed by. And so this is delta z, how much the z changed by. And then likewise, what you can do is just like in the previous picture now, we could form this right triangle here, like that, to give us to help us find L. So that'll end up being in this case a little right triangle right there. Okay, and it's a little hard to see at first, but what's going on from here to here, those are going to be how much the x is changed by, and these are going to be how much the y is changed by, like that. All right, and so this leg right here would be x1 minus x naught, and this leg right here would be y1 minus y naught. All right, and so long story short, we go through the same process. If you want me to go through it more carefully with you, we can. We could say that the distance is x1 minus x naught squared plus y1 minus y naught squared plus z1 minus z naught squared. Okay, and that's the distance formula in 3 dimensions. All right, and so again, make sure you realize in 2 dimensions we just have these 2 parts, the x's and the y's, so this formula extends naturally to 3 dimensions. One other thing too, just about calculating, since we're squaring inside of here, it doesn't matter what order you write things in, and make sure you realize these are just changes in coordinates. And so a way that I like to think about the distance formula is that it's delta x squared plus delta y squared plus delta z squared. I didn't write that last part very clearly, did I? Like that. Okay, and that'll help you understand a calculus concept. Hopefully it'll help you understand a calculus concept that we'll deal with later called arc length, because the formula that we use for arc length basically comes from this idea right here, whichever way you look at it. All right, so that's the distance formula for 3-dimensional points. Okay, so hopefully you're seeing the idea that these geometric formulas extend to 3 dimensions. So I'm going to keep this one a little bit brief and give you a link if you're interested in how to derive this. But we're talking about the midpoint of 2 points. So same idea, we have these 2 points somewhere out in space. And then the idea is that I think about connecting them with a line, and then I want to find the point that's halfway in between them. Okay, like that. And we call that the midpoint. And I'll usually just abbreviate it as MP. All right. It's very interesting that you would think to derive this formula you would need the distance formula. Okay, and so it's very interesting, but you don't at all. And the point is, and let me put up this link if you're interested in and a derivation of this, but this was the first video that I found, but it was a very good explanation. But the idea behind the derivation, now this video goes through it in 2 dimensions, I'll mention too. But the idea is that you can form these 2 triangles right here between the midpoint and the 2 endpoints like there, and those triangles end up being congruent, and you can take advantage of properties of these lines being parallel and the congruency to derive this formula. Okay, but anyway, one important thing too is with the last formula, it was the distance, so that was a single number. Make sure you realize for the midpoint, we're actually finding a point, and so it will actually have 3 coordinates just like the given points. That's a common error for people to make with midpoint, is they try to convert it into a single number. Okay, but the idea here is that in 2 dimensions, if I didn't have those z coordinates, then there is a midpoint formula. I don't really like to think in terms of formula because there's a nice concept to notice from the formula. But in 2 dimensions, we get x naught plus x1 over 2, and then y naught plus y1 over 2. That's the formula in 2 dimensions. Make sure you realize if I just have 2 numbers and I add them together and divide by 2, that's their average. So it's the average of the x coordinates. Same thing here. This is the average of the y coordinates. Okay, and so then in 3 dimensions this formula extends, and so we get z naught plus z1 over 2, like that. And this thing's called this, so that would be the average of the z coordinates, like that. So whenever I think about the midpoint formula, I don't think so much about the actual formula. It's easy to forget. And the reason it's easy to forget is that for the distance formula, we have subtractions in the formula, if you look at that back at the last slide. But in the midpoint formula, we're adding. And so I usually just think of average of the x's, average of the y's, and average of the z's if there's a third coordinate, because I know how to compute averages easily, and I'm not tempted to make that silly mistake of accidentally subtracting instead of adding whenever I do that. All right, so that's the midpoint formula, and make sure you realize this is just a nice thing that people forget. If you're only in 2 dimensions, it just doesn't have that third, so you're really seeing 2 formulas at once right there. All right, and just try to take advantage of this. Why don't you pause after you see what to do? Why don't you pause and just practice? Make sure you have this, because it's just easy to spot little silly mistakes that our brains make on us. And so please pause and try these 2 and then see if you end up getting the correct answers. Okay, but in each one of these problems, we're given 2 points, and we want to find the distance between them and the midpoint of the given points. Okay, and so for the distance, if you're using the formulas, this is our x naught, y naught, and z naught. And this is our x1, y1, and z1. Okay, so for the distance, it's the square root of the change in the x's, so 3 minus 1 squared, plus the change in the y's, so that'd be 6 minus 2 squared, plus the change in the z's, which is 4 minus 3 squared, like that. All right, and now we just need to compute, and so we have the square root of 3 minus 1 is 2, so we have 2 squared, plus 4 squared, plus 1 squared. That's going to be the square root of 4 plus 16 plus 1, and so that's the square root of 21. Okay, so the distance between them is the square root of 21. All right, and then for the midpoint, remember this is a point, so it's going to have an x, and y, and a z coordinate, and all you do is average each of the x coordinates together, you average each of the y coordinates together, and you average each of the z coordinates together, like that. And so we end up with 4 over 2, which is 2, 8 over 2, which is 4, and 7 over 2, which we could write as 7 over 2, or 3.5, or 3.5, however you want to, but that's the midpoint there. So hopefully you got those. If not, make sure to look back over and see where you went astray. Okay, on this one, it's very similar. It's just I wanted you to get some practice with negatives. But in terms of the distance formula, again, you can label your things here like that to help you if you need to. Okay, and so for my x's, I have -1 minus 3 squared plus, then I have 6 minus -2 squared. So be careful with signs whenever you have those negatives. And then for the changes of z's, I have -3 minus -4 squared. Okay, and so -1 minus 3 is -4. Then I square it, I get positive 16. And then, so this is -4 squared. Okay, remember to square that negative. And then we got 6 minus -2, that's actually 8 squared. So that's going to be 64. And then plus, we have -3 plus 4. So that's going to be +1 there. So we get +1. Okay, and we have 65 plus 16, which would be 81. Oh, interesting there. I just made that problem up. And so we have the square root of 81. Here our distance comes out to be a nice whole number. Okay, and so we get the distance is equal to 9. All right, and then as far as the midpoint goes, then remember we have a point and we just average the x coordinates together. We average the y coordinates together. And we average the z coordinates together. Like that, and so we have 3 minus 1, which is 2 over 2. That would be 1. And then we have -2 plus 6 is 4 over 2 is 2. And then -7 over 2. That's interesting too. I really just made up these two problems off the top of my head. And in the first problem we got on our z coordinate +7/2, and on the second one -7/2. Okay, so that's going to be it for our intro to three-dimensional coordinates. I hope it makes a little bit of sense. You'll see once you're trying to draw, that's really the hardest part, is getting down drawing in three dimensions. But most formulas just carry over from their two-dimensional analogs, as we saw. And so that's a nice thing. And so the hardest parts about three dimensions, at least to me, is drawing. I can't draw very well in three dimensions. And then learning, especially for the people that can't draw very well, but for everyone, learning to visualize mathematical objects in three dimensions. And that was a big skill that I learned whenever I took the classes. I couldn't convey it on paper very well, but I developed skills to be able to try to see it in there, and that's one thing you want to try to do. Okay, so I hope that helps, and I wish you the best.